The second example is a little bit different, but we just got to be careful of what we're given in this question. We're given power. A 6 watt, I guess it should be 6 watt light bulb with a wavelength, or emits light with a wavelength of 5.00 times 10 to the negative 7 meters, is used for 2 minutes. How many photons are emitted? Well, we're given power equals 6.0 watts. We're given wavelength 5.00 times 10 to the negative 7 meters. We're given time. Now I'm going to change 2 minutes right into seconds already. 2 minutes, which is equal to 60 seconds in a minute, 120 seconds. And what we're being asked for is the number of photons. Now be careful. Remember, the bulb or whatever the device is that's emitting this light is emitting many photons per second. Each one has a specific energy according to Planck's formula. So the power will describe the energy of the device. A 6 watt light bulb, a 60 watt light bulb, a 100 watt light bulb, whatever. The power describes the energy being emitted, total. Planck's formulas will calculate the energy of the individual photon each one carries. So we'll be able to find the number of photons by taking the total energy emitted by the device, dividing the energy each one carries, and we'll know how many we have. It's like finding cost per unit kind of thing, how many units you have. We're just dealing this with a physics concept. So I look at off our data sheet, power way back when is equal to work over time, or power equals change in energy over time. And this is for the device. So we can manipulate this and say the amount of energy being emitted is going to be the power of the device times the time interval we're measuring from. So change in energy is going to equal to 6.0 watts times 120 seconds. So we should get in 2 minutes 120 times 6 will give us 720 joules of energy. So there are 720 joules of energy total being emitted in 2 minutes. What we want to do is, since we know the wavelength of the photon, we can find the energy equal to hc over lambda, and this is the energy of one photon. So we can find the energy per photon using this formula. Well, Planck's constant, since we're dealing with total energy in joules, let's use Planck's constant with joules. That is 6.63. This is off my data sheet again, times 10 to the negative 34 joules seconds times the speed of light, 3.0 times 10 to the 8 meters per second, divided by the wavelength of this particular substance. About green light, basically. This is a green laser. 5.00 times 10 to the negative 7 meters. If we punch that in, 6.63 to the exponent negative 34 times 3 to the exponent 8 divided by 5 to the exponent negative 7 should give us 3.978. And I'm not going to round yet because this isn't what we're looking for, times 10 to the negative 19 joules. And I'm just going to go down here, joules per photon. That's really what it means. people really struggle with this question, and you actually do calculations like this all the time when you want to find cost per unit of some item. You're just dealing this with a physics concept. Like I said earlier, it seems a little bit different. But we find the total, we find the amount of energy per item, per photon, and then to find the number of photons, we just got to do one more calculation. Number of photons, this isn't on your formula sheet. It's going to be take your total energy, 720 joules, divided by the energy per 3.978 times 10 to the negative 19 joules per photon. Notice all you get as units after is units of photons. So if you go 720 divided by that answer, you end up with 1.81 times 10 to the 21 photons. That should make a lot of sense because we've already talked about in the lesson how much energy these represent. These are tiny, tiny increments of energy. So when you're trying to picture quantum physics, it's really hard because the objects we're talking about are not everyday type of objects. We're talking about incredibly small amounts of energy, things you cannot see. That's why things appear continuous. But in reality, what's happening is these are actually little tiny chunks that look continuous when you have a large scale, but on an atomic scale, they are not. It's discrete. And that's why in the lesson, the one way that I could kind of describe it, and it's not the best way, is to think of drawing a line on a computer. The computer will recognize that line as a series of dots that are very, very close together. In fact, so close together that when you look at it at your scale or your macroscopic world, it appears to be a continuous line. Well, that's what energy of light is. It is a series of tiny, tiny little specks of energy that are moving from one place to another. Whether it's light or whether it's matter does not matter. That tiny little bits of energy are so small we can't see. So according to our scale, it looks continuous. This is why it was such a revolutionary concept. This is why quantum physics is so hard to wrap your head around, is it's pretty difficult to see this in reality. Anyways, this is how you would do a calculation with power. Very common type of question that you see on diploma exams.